So thank you for joining us. We're going to find out what Industry 4.0 is and how we can have applications of the concepts. This is a team from Dr. Sam Remet.
Thank you, Dr. Milton. Hello, everyone, and welcome to our senior design presentation. Our project was the application of Industry 4.0 concepts. Team members and presenters for this project are Paige Lipinski and Stephen Satari, with project advisor being Dr. Sam Remet. There we go. All right. Great start. A little bit of background on our project. In Dr. Sam's EDMM 4560 process testing and measurements class, there are 2 test stands down in the Foundry Lab that represent different types of manufacturing systems. The purpose of these test stands are to demonstrate how to collect data from processes in order to conduct process control tests. These test stands, however, currently rely on manual techniques in data identification, collection, calculation, and analyzation in order to perform these said process control tests. So the purpose of this project then is to take these analog methods of data collection and transition them into using a digital data acquisition or DAX system. So in order to achieve this, we need to apply the new age way of thinking about manufacturing, which is Industry 4.0. But for those not familiar with this new discipline of engineering, what does this mean for manufacturing as a whole? Industry 4.0 is what's being referred to as the 4th industrial revolution, where computer age technology is being applied to manufacturing systems in order to make products quicker and more accurately than ever before. There are 9 key pillars to Industry 4.0, as you can see up here, but the 4 that we'll be mainly focused on for this project are Internet of Things, big data, automation, and simulation. So with these concepts in mind, the goal of our project is to design processing systems that can be monitored remotely in near real time using cyber-physical devices, which is any sort of hardware that is being controlled by a computer program, such as like the autopilot on an aircraft. It is imperative to these systems that the data collected is in near real time as possible, and not old legacy data that no longer represents the current process parameters that it's operating at. To achieve this goal, our objective for our project is to modify, install, and program process sensors into 2 systems that can send data to a digital data acquisition system for a continuous system, which we refer to as the water system, and a non-synchronous system, which we refer to as the ball system. The deliverables for this project are 2 modified test stands that can display data in an easy-to-export database system, such as Excel. The constraints of this project, however, are that any modifications made to the test stands have to be, can't make any, can't interfere with the process in any form, and have to act as passively and contactless as possible. Any modifications also have to allow the system to operate continuously without human input, as if there is no one present in the lab at the time it is running. This project has a heavy reliance on coding, which neither group member started off this project with a lot of, which was a learning curve for both team members. Finally, we had to work around a rough budget for this project, which means we had to be conscientious about how much these components cost and use best practice methods when ordering these components to the system. The reason for this project is that it will improve the efficiency of control tests in a process control class. Because the data represents the processes as they are happening, minor adjustments can be made to these systems in order to produce a better product. This will also allow processes to be run remotely, which combined with remote control access to these systems will allow the processes to run while no one is in the physical plant, such as during an overnight shift, which will allow for longer production times. Lastly, and most importantly, this will give Western students hands-on examples of Industry 4.0 concepts and not just theories they hear about in class. This would take the form of students learning how to utilize the software in data collection and the steps to assemble a data acquisition system to a manufacturing process. This will give students industry experience and the ability to make the critical decisions in deciding on how a company operates. All throughout our project, we applied the concepts of the engineering design process wherever we could. The first step in our project was to define our problem statement, which is that we want to upgrade test stands in a process control class with a digital data acquisition system in order to improve the accuracy of process control tests. Once we defined this question, we researched different types of process sensors, controller boards, and techniques for data acquisition. We then compared these alternatives for each identified subcomponent and compared it to how they would achieve the goal of our project. Once an alternative was chosen and purchased, we assembled and wrote code for each of these subsystems and tested them individually to make sure that they met the needs of our project. We then assembled the subcomponents to the overall system and tested the systems to see if they met the problem statement. If they didn't, we defined a new sub-problem statement that asked why these didn't function in the way that they were supposed to and restarted the design process. Once we got systems that achieved our problem goal, we handed these materials back to Dr. Sam and gave our future recommendations. I'll now pass the presentation over to Paige for future methodology.
So the first test stand that we worked on is known as the water system. The key feature about the water system is that it's a continuous process, meaning it's producing product continuously, like an alloy mixing furnace or an assembly line building cars. So how it works is water will enter up into process 1, and then it'll go down and split into 2 parallel processes where the water is heated to different temperatures as well as flow rates. And then the water will mix down into process 3 for a final product. Flow rate and temperature are both being taken into the parallel processes, as well as additional temperature being taken in process 1 as well as process 3 with additional ambient air temperature. Right now, at the time, we were using thermocouples that were able to send the temperature data into an Excel sheet. And then the way we were collecting the flow rate was by hand writing down it from the mechanical flow meters that were already installed into the system. So here's the process control charts and graphs used for heater 1 and 2. The graphs are to show the average temperature and then the average moving range of the temperature. Data was collected every 5 minutes or 75 minutes by recording the current temperature from the moving temperature graph that was used. As you can see, all the data is within control. It's not going above or past the upper or lower control limit. But also on this graph over here, you see the time in red that was already taken, but then we had to calculate by hand the mean, upper control, lower control, everything else that's on that graph, and by hand had to make the graphs by hand. Actually, this was homework taken when me and Steven took the class last year. These are the charts that we had to calculate and then the graphs that we had to do by hand. So what are the problems with the water system? First off, the old thermocouples are hooked up to an old digital data acquisition system that won't be able to install other sensors to it or be able to send information to other computers. Also, we are using manual flow meters, so all the flow rates being recorded by hand, so we have to somehow make those digital. Also, right now, students are doing calculations by hand, like you saw in those charts. A lot of them were done by hand, so it's prone to human error. And then also requiring manual setup for those control charts, which also led to human error as well. So these are the ways we had to fix it. First off, we had to replace the old thermocouples because the old ones wouldn't be able to hook up to our new digital data acquisition that we picked out. Also, these ones are waterproof, which is really important because the system runs through water, but also they're very accurate in collecting data as well. Then we replaced the old manual flow meters with these digital flow meters, 3-wired flow meters. The reason we chose this one was because we needed to relatively read small increments of volume. So this one's able to read between 0.3 to 6 liters per minute. And also we needed to be able to install to the 1/4-inch inner diameter tubing that we have already installed into the system. So once we had our sensors picked out, we then had to pick out a digital data acquisition system to be able to record the data. And we chose the Arduino board. The reason we chose the Arduino board is because it uses a common programming language like C++, Python, or Java. It's versatile, it's easy to use. And also the big thing about the Arduino board is once we had a code finalized, you're able to store that code into the Arduino board. So you can have a computer come up, hook up to it, collect data, and then unhook it, and then go get a new computer, hook up to it, and be able to record data again without even having the code installed into the computer at all. So once we installed the sensors, we then had to wire them back to the Arduino board. Since we're using multiple sensors, we figured it'd be best to feed it into a breadboard so that way it wouldn't overcrowd the Arduino system. Also, the breadboard helps if you want to install other sensors down the line, you're able to. Since the sensors weren't long enough to reach back to the breadboard, we had to crimp wires together to be able to make them to the desired length to reach back there. So once we had that, we then had to look at coding. Since Arduino is using more of a common coding like Java, we were able to look online to get a good basis of how to start the code. And then along the line, Steven did have a coding background. He did a little bit of class and it started coming back to him more. So he was able to modify the code, put in different things, take away different things. Like one of the big things was the flow meters were already reading in liters per minute, but Steven changed it to cubic centimeters per minute. So for Dr. Sam's class. We also installed a programming library for the thermocouples because they needed a more advanced code to display the data and capture the data that we were looking for. Then we met with Mr. Jason Johnson, who is part of the computer science department, and helped finalize the code and make sure it was reading the data that we were looking for. So after installing, replacing, wiring, and coding, this is what the new water system looks like. As you can see, we repainted it, added new labels, changed out the old tubing, did some cable management. But we also color coded the different areas for testing later, which we'll see later. So like process 1 is black, one of the parallel processes is red, the other one is green. Process 3 is blue, and then the ambient air temperature is purple. So once we got this up and running, this is what we are able to test. We have the data being able to feed into an Excel file under the data streaming tab. The reason we use that is because it's able to hook up to the Arduino board and get the data. This is a video of the data being taken, but like this is what it would look like if you're actually getting the data in real time. We have the flow meters up and running on the left side, and then we have all the temperatures color coded as you saw in the photo before. So that way it's easier to follow a certain temperature or a certain flow rate as needed. Now having all these numbers is great and all just to look at, but we took the last 15 points and created a graph to show the data. The reason we took the last 15 points is because it's the minimum number needed to accurately calculate a standard deviation. But also this graph has helped to show if any trends happen, like any increases, decreases within the system. And it's all color coded, so you're able to pick out a certain temperature and follow it. We did the same thing for the flow meters. Took the last 15 points, have it color coded so you can follow a certain flow rate, but also it's to help show any trends that may be happening within the system. So water system results, we are able to finally capture flow rate digitally. We're able to collect data every second, which is important to do process control tests. The more data, the more accurate your process control tests are going to be. Graph to show trends. And the biggest thing is we're able to stream the data through Microsoft Teams. So a student can be able to look at the data and capture it from being somewhere else in the building, somewhere across state, or even across the country. They just have to log in the Teams, stream it, and then collect the data as they're doing it. So the next system that we looked at was the ball system. So opposed to the other one, this one is known as a non-synchronous process, meaning it's producing product randomly based off small variations within the process, or a ball rolling through and stopping at various intervals, or like how a restaurant makes food on demand as it's being ordered. So how it works is when the system's running, multiple balls will roll through the track, stop at 5 different processes, plus inspection and then storage. In order to do process control tests, students have to take a video of the system running and then have to do questions later, which this is the system running. A student actually took it this semester, and this is the video that they took. So they have the video running for about like a minute, and then these are the questions on the right-hand side that they have to answer. Some of them are pretty easy, like how many balls went into final good. So basically, it's asking how many balls went from the beginning to the end. But then there's some questions that are a little bit harder, like did any defective balls move into finished goods? Like we don't have any real numbers on exactly how the ball is considered a bad good or a bad product. Like all we know is just the balls are rolling. There's no way we know how much it weighs or like how fast they're rolling through the system. We just look at it and it's like, this looks good to me. Another big one is doing calculations, like calculating the average time and variable of each process. That takes multiple takes because you just have a video, so you have to go through and make sure you're statistically getting enough information so you're able to have an average time. So ball system problems. First off, it's not collecting any hard data or numbers, just rough information on where the balls are within the system. As shown in the video, it's not straightforward or easy to follow the balls or track the balls visually through the system. If you miss one ball, like you have all your calculations for your homework are not going to be accurate at all. or you just might not even be able to finish the homework. It was a headache. And then most measurements have to take several takes to make sure the data obtained is accurate, which means about 3 times for most statistical methods. Also, as you probably saw in that video, you're only able to see the front side of the video. And most of the processes have the ball exiting from the back side of the process, so you don't get a real idea of when the ball is actually leaving the process. Another big thing is doing calculations, manual timing calculations. They're all done by hand, which is going to lead to more human error. These are all very inefficient ways to collect data, because by the time the operator comes to a conclusion, the ball system has probably already ran like 3 or 4 more takes, and then by the time, and so the process variations have changed enough that the conclusion that the student or operator has already come up with is very irrelevant at that point. So we had to figure out a sensor that would be able to capture the data, and we came up with infrared sensors. We'll have 12 infrared sensors along the track that will indicate when the ball enters the system, enters or leaves a process, or when the ball leaves the system. The IR emitted LED light will flash red when the ball rolls by and triggers it. The reason we chose the infrared sensors is because it's able to indicate or detect the ball up to a certain narrow window and be able to record the information. Also, they're small and lightweight. But since the infrared sensors are only able to indicate up to a certain distance, we had to figure out a way to hold the sensors along the track. And we decided to make 3D printed brackets. The 3D printed brackets will hold the sensors along the track without interfering with the system or the balls. The reason why we chose 3D printed brackets is these 3D printed bracket had to be designed to a different length. So make sure it wasn't interfering with the system, but also was able to capture the data we were looking for.
I must just throw I apologize. The screen on mine is not matching.
Oh,
Can you? I think we'd like to see too. There's a lot of people online.
okay.
Are we caught up now online? Okay. I apologize.
No, you're good.
Thank you.
Yeah, no. Okay, 3D printed brackets. So it's able to hold the sensor. Another reason why we chose 3D printed brackets is because they don't need to hold a lot of weight since the sensors are small. It would be beneficial if they were light as possible, which the plastic provides us. The way we designed these, we took the measurement from where we wanted to install the brackets to where we wanted to hold the sensors along the track. And then we designed the brackets in an Inventor, which is a CAD software. And then we met with Mr. Alan Carl, who runs the 3D printers in the college machine shop, and got them 3D printed for us. So since we're already using the Arduino board as the digital data acquisition system again, as the same for the water systems, easy to use, easy to code, we went back to coding the ball system. Stephen was able to create a code that's able to indicate when the ball enters a process or when the ball leaves the process and then going to another process. So this is the modifications to the SAM. We were able to install the brackets, the sensor, add new labels, did some cable management. But now you can see in the video, as the ball rolls by the sensor, it'll flash off. We did have to make them a little bit narrow because multiple balls go through the system, and sometimes they're a little too fast for the sensors to keep up. So we had to restrict the sensitivity or make it more sensitive so it's able to detect those multiple balls. So yeah, as it's going in, it's all feeding into that computer down there, into the Excel sheet. This is what it's looking like. So as the ball enters the system, you can see it tick up, but then when it leaves into process 1, it'll tick up, and then that process will tick down. And then it'll tell you the total side on the right side of the Excel sheet, the total balls in the system. So right now we have 3 balls, and it'll indicate how many balls are in as it keeps coming up. And then we do have a timer over here that indicates how long it takes from process 4 to process 5. We did do some statistical methods, and it usually takes about 2.7 seconds to about 3.5 seconds to get there. So any time that's like longer, like 7 seconds or so, or 5, it's considered a bad product. So ball system results, we're able to detect balls up to a certain section or different process, or how long it takes from one process to another, able to detect if the product is either good or bad. And then we're also able to stream this data through Microsoft Teams as well for the same reason as the water system. Now I'll pass it back to Stephen for conclusion.
Thank you. So after testing both of these systems, here are our final conclusions based off of the project goals that we outlined at the beginning. Both systems are able to read data continuously for several hours without human input. and is able to store this data in a database system for future process control testing. The data collected is both being taken more quicker, which means more data points, which means more accurate process control testing can be done on it, and is able to be done more accurately, as in operators no longer have to approximate what values are, such as the flow rate or when a ball enters or leaves a process. The data is also able to be better visualized, as it is all collected in a singular location and is color coordinated so that an operator can identify different variables for process testing quicker. And the data is able to be remotely streamed and accessed by students from a computer anywhere. So they no longer have to be in the physical room in order to conduct these labs for this project. Now that we have accomplished our goal, we also outline some recommendations for future projects in order to further the project in the goals of Industry 4.0. Now that the data is able to be collected automatically, the next step would be to automatically produce process control tests and charts based off this data. To this end, we're talking with a company called Altair that has a software package that's able to perform statistical analysis on these data sets in order to produce these data charts that can be visualized well with charts on their software. The software can also take the data being streamed on Teams and analyze it from any location, such as their office on the other side of the state. The next step would be to allow these systems to automatically react if a process falls out of control. For the ball system, this would take the form of allowing it to kick a ball out of the system if it detects any defects on the surface, which would take the form of how long it takes to go through various processes, as Paige outlined earlier. For the water system, this would take the form of heating or cooling one of the two parallel processes if it detects that the final product does not meet customer specifications at the end. For their help on our project, we'd like to thank the following people. Firstly, Dr. Sam Ratton, for our project advisor, for his continued help for both these semesters on all matters of subjects. Dr. Pavel Ikamanov, for his help on identifying process sensors and other physical to digital devices and data collection. Mr. Jason Johnson, for his help in debugging our coding, which was a major hurdle for us throughout the project. Mr. Alan Carl, for his help on 3D printing our mounting brackets for the sensors. And finally, the Altair team for providing testing on their software packages. We'd like to thank everyone for coming to our presentation. This has been a very insightful and intriguing project. We'd like to open it up now for any questions anyone may have.
Any questions in the room? Any questions? Oh,
If you were to scale it up to industry level, what your team will be different if you would scale it up to industry?
So if we were to scale up the project to an industrial level for like an actual factory for a facility, what we would do differently mainly is on how many sensors that we include in the system, because for most of them, they just had like a max of like 5 for the water system and 12 for the ball system. That have to probably be scaled up to probably several hundred sensors throughout various different individual processes that might have different metrics be measured, and several different metrics be measured. We'd also need probably some more accurate sensors. There's definitely more online, more expensive than what we got, that can read even more accurately to make even finer adjustments.
And probably want to feed it into an Excel sheet more advanced. Like
Yeah, I'd like to use an actual professional database system. I know there are a few out there that could handle those larger data sets even better than Excel. Because Excel, it does everything near real time, but it does lag slightly, and those kind of database systems would be able to react faster.
Can you explain how on a ball system your algorithm determines a bad ball from good ball?
So our system is able to determine if a ball is good or bad based off of how long it takes it to move through various sections of the track. So we took the measurement from process 4 to process 5, the length of the track, like material handling. Determined based on how long it takes a predetermined good ball to go down the track, which is usually the first ball, and set a limit to like how much variability a good ball would have to go through that project, because obviously they don't go through it at the same exact time. And any ball that either exceeds or doesn't meet that limit will be determined as a bad ball.
Any other questions, either in the room or online? All right, thank you, Keith. Thank you.